Dear students, welcome to this lecture on the stability of discrete systems. So, in this lecture we will see some results on the stability of discrete system which are analogous to the stability of continuous dynamical systems. So, earlier we have seen the continuous dynamical system of the form dx by dt is equal to a into x of t, where A is a constant n cross n matrix. So, the result the x of t identically equal to 0 is the trivial solution of this continuous system, and it is also called the equilibrium point. Equilibrium point of the dynamical system. So, the stability of the system at this equilibrium point was analyzed using the eigenvalues of the matrix A. So, the result was, if all the eigenvalues of A has negative real parts, then the system is asymptotically stable, and if any of the eigenvalue have negative real part, a positive real part, then the system will be unstable, and if the eigenvalues are purely imaginary, in some cases we can see that it will be stable. So, there are some special condition on that particular case where the eigenvalues are imaginary. So, depending on the algebraic and geometric multiplicities, we can decide the stability or instability of such systems. So, here those results have been earlier seen while dealing with the continuous dynamical systems. So, analogous to those results, we can see some result in the case of the discrete systems. So, let us consider the discrete system x of k plus 1 equal to a of k x of k for various time instances. We can say k equal to k0 plus 1, etc. And it can be easily seen, if x of k is equal to 0 for all k, and if you substitute it in the right hand side, we will get x of k plus 1 is also equal to 0. So, we can conclude that the 0 x of k is identically equal to 0 for all k is a trivial solution of this system 1, or it can be called the equilibrium point. The origin is called the equilibrium point of this system. So, here A is a n cross n matrix, and x of k, it belongs to Rn for each value of k is the state variable. Now, we will state the definition of the stability of the system at this equilibrium point. So, here the trivial solution is said to be stable if for any given epsilon there is greater than 0, there exists a delta positive, such that whenever the initial condition x of k naught is less than delta, then the solution x of k lies within the epsilon neighborhood. So, here we see that if this is the state space, for example, in the case of 2 dimension, let us say x is equal to x1 x2, 2 variables are there, then for every given epsilon 0 is the trivial solution, x1 is 0, x2 is 0 is the trivial solution of the system. Then for every given epsilon, the radius of the circle is epsilon, there exists a delta greater than 0, we can find a circle of radius delta such that whenever the initial condition x of k naught is inside the delta circle, then the solution x of k for all the values of k afterwards. So, that will always lie within the epsilon circle. When we take the discrete points, because the solution is not a continuous one, x of k naught is x naught is a point, and then next point is x of k naught plus 1, that will be a discrete point. So, if we connect all the discrete points for each value of k, we will get a curve, we will get a discrete set of points, all of them will lie within the epsilon circle. So, that is the definition of the stability of the system. In addition to that stability, if you also have that x of k tends to 0 as k tends to infinity. So, as k becomes larger and larger, the initial point if you start, then for each value it will approach the origin. X of k naught is starting point and x of k naught plus 1, k naught plus 2, etc. These points finally reach the origin in the limiting case as k tends to infinity, then we say that the system is asymptotically stable. So, it is a similar definition that is analogous to the continuous case. Now, we will see the condition on the stability, condition on the matrix for the stability of this discrete system. So, let us consider instead of the time varying system A of k, let us consider A of k is a constant matrix A. Then we have already seen in the previous lecture the solution x of k is equal to a to the power k minus k naught into x naught. So, let lambda I equal to 1 to n be the eigenvalues of the matrix A. So, if A is diagonalizable, then we can find n linearly independent eigenvectors corresponding to these eigenvalues lambda I. So, let us say x1, x2, xn are the n linearly independent eigenvectors which satisfy the equation like this: A xi equal to lambda I xi for I equal to 1 to n, standard definition of eigenvalues and eigenvectors. Then multiplying repeatedly, we can easily see that a power m xi is equal to lambda I to the power m into xi for I equal to 1 to up to n. So, this is for any positive integer m, this satisfies. And because we have n linearly independent vectors in Rn, it will form a basis in Rn. So, any vector can be written as a unique linear combination of the eigenvectors. So, initial condition x naught is a vector in Rn. So, it can be written as C1 x1 plus C2 x2 etc. Cn xn as given in equation 4. So, substituting that initial condition in the expression 2, that is x of k is a to the power k minus k0 into x0. So, in the place of x0, if you substitute equation 4, we get the expression like this, because a power m xi equal to lambda I to the power m xi. So, we can substitute using this, we get the expression x of k to be like this. Now, we take k larger because we are interested in k tending to infinity. So, we take k is greater than k naught and further it tends to infinity. And when we have k minus k naught always positive, and if the eigenvalues are such that modulus of lambda I is greater than 1, even if one of the eigenvalue have modulus greater than 1, we can easily see that it will tend to infinity. Lambda, for example, if lambda 1 is greater than 1, then its positive power will keep increasing and then it will tend to infinity. It implies that x of k will tend to infinity as k tends to infinity. So, for the stability condition we need that the modulus of the eigenvalue lambda I, all of them has to be less than or equal to 1. So, if the modulus is less than 1, strictly less than 1, we can easily see that the modulus of lambda I to the power any positive number, it will tend to 0 as m tends to infinity if this is less than 1, strictly less than 1. So, we can see that if all the eigenvalues have the modulus strictly less than 1, or if they lie within the unit circle, if we take the unit circle in the complex plane and if all the eigenvalues lie within the unit circle, then we say that the system is asymptotically stable. And if the modulus of the any of the eigenvalue is equal to 1, we can see that that particular term is always a constant. If you take modulus here and then if the modulus is equal to 1, a particular term is constant, and if the remaining eigenvalues are inside the unit circle, the remaining terms will tend to 0. So, we can say that the modulus of x of k, it may not converge to 0, but it will remain a bounded value, because C1 is C1, C2, Cn are bounded values. So, modulus of x of k will be bounded provided the modulus of lambda I or any sum of the modulus of the eigenvalues are 1. So, in that case we say that it is stable here. So, similarly in the case that A is not diagonalizable, we will get the Jordan canonical form. So, in that case instead of n linearly independent eigenvectors here, in the diagonalization case we will get n linearly independent eigenvectors, but in the case of non diagonalizable matrix we will get linearly independent eigenvectors. The number of linearly independent eigenvectors will be strictly less than n. So, we will be able to find the generalized eigenvectors and then we get a basis consisting of eigenvectors and generalized eigenvectors in the space Rn. Then the initial condition can be written as the linear combination of eigenvectors and the generalized eigenvectors, and the proof will be similar. Once we write the solution x of k in the form of equation 5 using eigenvectors as well as generalized eigenvector, then we will get the similar result, that if all the eigenvalues lie within the unit circle, it will be asymptotically stable, and if any of the eigenvalue lie outside the unit circle, it will be unstable, etc. So, this result is similar. Now, stabilizing using feedback. So, let us consider the dynamical system given in equation 6 here. If the matrix A is such that the eigenvalue, some of the eigenvalue lie outside the unit circle, then the system is unstable. Now, in order to make the system stable by applying a control term, so we can consider the control system x of k plus 1 is a into x of k plus b into u of k, where u of k is the control variable for various values of k. K is initial condition is k0 plus 1, etc. Now, in order to make the system say asymptotically stable, so we want that x of k should tend to 0 as k tends to infinity. is the requirement for asymptotically stable system. We have to select the control u of k in a special manner, so that the system becomes stable or asymptotically stable. So, this procedure is again similar to that of the continuous case, as we have seen in the feedback control lecture, that we can find a feedback control u of k such that u of small k, it is some matrix k times x of k, where k, this is a m cross 1 matrix and this is a n cross 1 matrix. So, we will get m cross n matrix. The k matrix is m cross n, and so we have to find a m cross n matrix k such that A plus B k has all the eigenvalues within the unit circle, so that the resulting system x of k plus 1 is, so x of k plus 1 is A x of k plus B u of k, and if you substitute u of k to be k times capital K times x of k. So, we get a simple system like this, and if all the eigenvalues of A plus B k has modulus less than 1 or they lie within the unit circle, then we can say that the system is stabilized. In that case, x of k will converge to 0 as k tends to infinity. And the procedure is exactly similar to the case of continuous system which we have seen in the feedback control. Now, another analogous theory, that is, we have seen the Lyapunov stability theory for the continuous system, and if you have dx by dt is equal to f of x of t, where f of 0 equal to 0. F is a nonlinear function such that f of 0 equal to 0. This will imply that x equal to 0 is equilibrium point of the given continuous system. So, to analyze the stability of the system at this equilibrium point, we have seen the Lyapunov theory, that is, if there exists a Lyapunov function v, that is v is a positive definite function, that is v of x is strictly positive for all x non-zero and v of 0 equal to 0, and the derivative of v with respect to t is negative definite, then the system is asymptotically stable. So, that was the Lyapunov stability theorem for asymptotic stability, and if dV by dt is negative semi definite, then the system is stable. So, this result we have seen in the stability lectures. Now, we will see a similar result for the discrete system. So, a function v of x of k is called the Lyapunov function if for some r greater than 0, the radius r greater than 0, v of x of k is greater than 0 and v of 0 equal to 0 for any sequence x of k within this circle of radius r. So, let us for simplicity assume that the vector x is in R2, x is x1 x2, x of k is x1 of k, x2 of k. So, this is a state space. Now, if you take a radius r, a circle of radius r, and if x is within this circle x of k, then v of x of k, so we will get the surface x1 x2 is this, and then the value of v of x of k. So, if the radius of this circle is r in the x1 x2 plane, then corresponding to each value of x1 x2 within this circle, we will have a positive definite function. So, which represent the surface v of x1 x2. The surface is given by v equal to v of x1 x2 within the circle of radius r. So, if there exists a r satisfying this condition, we say that it is a Lyapunov function, and we will see the result on the stability of the system, autonomous system. So, if we consider x of k plus 1 is a non-linear function k and x of k, then it is called time varying system, that is non-autonomous system, and so this is non-autonomous. And because k is appearing explicitly in this equation, and if you have the equation like 9, x of k plus 1 is f of x of k, where k does not appear explicitly, but it can appear in as a part of x of k, then it is called the autonomous system. So, the system here 9, actually it is 9, the system 9 is stable if the trivial solution, the system 9 is stable at the trivial solution if there exists a Lyapunov function as defined earlier, and del v of x of k, that is the increment of the function v, okay, at x of k. So, that is given by v at x of k plus 1 minus v at k, the increment, if it is less than or equal to 0. In other words, v is a decreasing function in with respect to the variable k here. So, if this happens, then we say that the trivial solution is asymptotically stable, and if it is less than or equal to 0, then it is, the system is stable. So, it is analogous to the continuous case. In the place of negative semi definite, we have that the increment is less than or equal to 0, and in the place of negative definiteness of the function v, we have the increment is strictly less than 0 for any sequence. So, basically both of the conditions are very much similar to that of the continuous case. So, similarly the proof of this Lyapunov theory is exactly similar to that of the continuous case. Only thing is, in the continuous case we will have the continuous function x of t, and in the discrete case we have the discrete sequence, the points x of k at discrete points. So, the result is similar, the proof is also similar here. So, now let us see a simple example to illustrate the theory. Consider the system x1 k plus 1 equal to minus x1 of k plus x1 of k x2 square of k. and x2 of k plus 1 is x2 of k x1 square minus x2 of k for various values of k, all integer values of k. And it can be easily seen that when x1 and x2 both are 0, then it satisfies this equation. Therefore, 0 0 is the trivial solution or the equilibrium point. Of the system. So, if we consider the Lyapunov function v of x of k, that is v of x1 x2 is x1 square plus x2 square for each value of k, then it is easy to see that it is positive definite, all strictly greater than 0 if x1 x2 is not the origin, and at the origin it is 0 value. And the increment del v x of k, if you substitute directly, that is v of x of k plus 1 is x1 square k plus 1 plus x2 square k plus 1 minus v of x of k is x1 square k minus x2 square k. So, this expression from the given equation, if you substitute for x1 k plus 1 and x2 k plus 1, we get this expression, and further by simplifying we get del v of x1 x2 is strictly less than 0 provided these quantities are positive, that is x2 square is less than 2 and x1 square if it is less than 2, then we will get strictly less than 0 sign, or in other words if x1 and x2 lies within the circle of radius 2, then also we can say that the right hand side is strictly less than 0. So, according to the definition, the value r, we have seen that if there exists a circle of radius r in which these conditions are satisfied, then the system is asymptotically stable. So, this illustrate the asymptotic stability of this the Lyapunov theory. Okay. So, with this we conclude the stability concept for the time invariant system for the discrete dynamical system. Okay. Thank you.